Hey everybody, welcome back to another round of physics, and yeah, let's get going. Last time we discussed and introduced Gauss's law for the electric field and gave some examples of how it could possibly be useful, namely when there is a highly symmetric charge distribution. And that will avoid having to do double integrals and some other stuff, and rather we can use Gauss's law to shortcut to find the value of the electric field. Now, there's another place where Gauss's law comes in particularly handy, and that is when we are dealing with conductors. So the first thing that we should ask ourselves is, what defines a conductor? Yeah, good. The idea is that we classify materials as conductors when charges are easily allowed to move throughout the object. Now, the next question is thinking about a conductor for a moment. Okay? What is the electric field inside the body of a conductor? Yeah, good. Hopefully, you can argue it mentally that the electric field inside the body of a conductor must be zero. Imagine for a second, let's do a proof by contradiction. Let's imagine for a second that the electric field inside a conductor is not equal to zero. Then, if the electric field inside a conductor is not equal to zero, imagine for a second, what will the freely moving charges, generally electrons, do inside the conductor? Yeah, good. If the electric field is non-zero, then these charges will move around, right? The electric field means that there is some force acting on each of those electrons equal to negative E times the value of the electric field. And so those electrons will accelerate. They'll move around. Now, the next question, at what point will those electrons stop moving? I'll put it in quotes, like stop moving. Good. Hopefully you see that if the electric field is non-zero, then the electrons will move around in the conductor, and they will keep moving around in the conductor until they reach a point when the electric field is zero again. Oh, wait, there's more. Field. Imagine for a second, I will take a Gaussian surface in green, okay, and I will make it so that that Gaussian surface is just right below the surface of the conductor. In fact, you can think of this as being just a tiny bit. There's a gap between my Gaussian surface and the surface of the conductor, just a really tiny gap. And because the electric field inside the conductor has to be zero, okay, that means how much charge is contained inside that Gaussian surface. Yeah, by Gauss's law, if the electric flux is equal to zero, and Gauss's law tells us that that is proportional to the amount of enclosed charge divided by epsilon naught, that means that the enclosed charge must also be equal to zero. Pretty cool, huh? If I take a conductor, no matter what it is, and dump some charge on it, I am insured both by the nature of what it means to be a conductor and Gauss's law for the electric field. I am insured that all of the charge resides on the surface. Well, let's try some other example problems. For example, here, I have a conducting shell. In other words, something that's spherical made out of conductors, but then I've drilled out a void in the middle. So this material in the center is not conducting. Okay? And for argument, we have the outer radius of that shell that I've called capital R. Okay? Well, let's say we could draw a Gaussian surface inside the volume of that conducting shell. And by nature of it being a conductor, we are ensured that there is no electric field inside that volume, right? Well, that means that the electric flux through that Gaussian sphere is zero. Again, this is because the electric field is zero. And therefore, there is no charge contained inside. And I should say, no net charge. Right? Well, if there's no charge contained inside, that also means that if I choose some field point that's a distance, much less than r, there's no charge in there either. Pretty cool, huh? Again, all of the charge ends up being on the, I should be more specific, the exterior surface of the conductor. You could say, well, this is an interior surface. Maybe it distributes there. Oh, nay. Gauss's law can be used to show that there is no charge on the surface, that interior surface. Pretty cool, huh? And in fact, this is such a well-known property that sometimes it's given its own name. Sometimes it's called the shell theorem. Shell theorem. And in fact, there's two versions of the shell theorem. This is the first, so number one. And it states, the shell theorem states verbally, that when you are inside a uniform distribution of charges, okay, so uniform distribution of charges that's spherical, the electric field has to be zero. Could go a little further than that. You could say the Coulomb force is also equal to zero. Okay, so no, pretty cool, huh? Well, how about this? How about if I'm outside that spherically symmetric charge distribution? So let's say now that I have some field point way out here at a distance r, which is larger than the radius of my shell. Go ahead, take a minute, see if you can come up with the answer. You got it? Good. Now here, we aren't familiar with the value of the electric field. That is, now that we're outside the conductor, we don't know what the value of the electric field actually is. However, we do now have an idea about how much charge I have enclosed. We have that 3e. So now we will use Gauss's law for the electric field to determine the strength of the electric field. Namely, we know that the flux must be equal to 3e over epsilon naught. And because of that, and we'll choose a sphere to match the symmetry of my charge distribution, we know that the flux will be something like the value of E times 4 pi, right? And be careful here. We're integrating over the radius of the Gaussian sphere. So right here I have two r's, the big R or the little r. What we mean is the little r. And so we have this equals 3e over epsilon naught. And so at the end of the day, we magically find out that the electric field due to this uniformly charged sphere, is 1 over 4 pi epsilon naught 3e over r squared. Now let that sink in for a moment. Okay? Because originally I emphasized that Coulomb's law for the electric field is only for point charges. But here we don't have a point charge. We have an actual distribution, a spherical distribution of charges. It turns out that when you have a uniform spherical distribution of charges, the electric field due to that distribution looks exactly the same as if you had a point charge of similar value located at the origin. In other words, rather than the 3e being distributed throughout the conductor, it's like I have a 3e point charge here. Okay. And that is known as the second shell theorem. Incidentally, because gravity is also an r squared dependence, there are also shell theorems for gravity. If I were to actually go and dig down beneath the surface of the Earth, okay, if I could get to the very center, the gravitational force acting on me would be zero because I'm inside all of the mass distribution. Similarly, if I am outside a uniform spherical mass distribution, I can treat it as if it were a point particle located at the origin, which is exactly what we've done in the past. Now, yes, we could prove this by simply chopping up the spherical distribution into tiny point charges, calculating the electric field due to each of those point charges at our field point location, and indeed we would end up with the same result. I will go ahead and save that for a different class. Not in this class, I mean like a different, class altogether. 332. Alrighty then. Okay. Well, let's go a little bit further. Let's say that there is a negative 2e charge brought near the conductor. Okay. And I want you to tell me what is the electric field at some field point inside the conducting shell. Go ahead, take a minute, see if you can hack it out. You got it? Good, 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 good. And you should have some sense. You know the answer, but it should feel kind of weird, right? In the sense of, well, we're still inside the conducting shell. I can apply Gauss's law for the electric field, and I get a net flux because I have no charge enclosed. I should end up saying that the electric field is zero. Okay. Cool. And incidentally, that applies to every location as long as I am less than the radius big R, which seems weird. You go, but wait, Greg, something has to change. There's something that has to change because that negative 2e charge has come into play. And I agree, there is. And good, you probably have a sense of it already. The thing that changes is not the amount of charge inside the conductor, but rather how the charge is distributed on the surface. Okay. So now we have to worry about effects like induced polarization. The fact of the matter that there's positive charge on my sphere and there's a negative charge, that means that more of my positive charge is going to congregate on that side. And then you can imagine because of that, we might have some negative charges congregating on the other side. So inside, incidentally, you say, how does it rearrange? It rearranges itself exactly so that the electric field inside is zero. Now outside, stuff looks different, right? If there's a reason why I don't ask you for the electric field at this field point outside of the sphere, because now we can't apply our shell theorem because the charge is not uniformly distributed on the surface. All bets are off on the shell theorem. In fact, I like to think of this. This is sometimes, this is the basis of what we would refer to as I'll call it electromagnetic shielding. From the standpoint of an observer inside the shell, the spherical shell, they have zero idea that that negative 2e charge even exists. Imagine that you are inside this closed room. Okay? You are measuring the electric field. It turns out that there is zero way for you to know what's going on outside because of that conducting shell. Okay, good. How about this? Let's say a positive charge is kept fixed. So now we have a conducting shell, and I have embedded inside that conducting shell, well, I say we have the conducting shell, and then inside the interior volume, I've placed another charge. Go ahead, get an idea about how the charge is distributed, both on the outside of the conducting shell, but also the inner wall. You got it? Yeah, good, good, good. And first off, you say because the positive charge is located at the center of the conducting shell, symmetry arguments would say that every piece of the interior wall should be the same as every other piece. And so we can immediately throw out, say, option A and option B. In fact, we could throw out option C too, just based on symmetry arguments. Every piece of the wall should look the same as every other piece of that interior wall. That means that option D is the only valid option. Sweet. Good? And again, I will remind you that the electric field inside the volume, inside the actual conductor itself, has to be zero. So not only can you tell me how the charge has to distribute on that inner wall, but you can tell me also exactly how much charge is there. Good. Negative Q. If I put positive Q in the center, there must be a total charge of negative Q on that interior volume. You say, well, how did you get that, Greg? And I say, well, let's go ahead and draw a Gaussian surface just inside the conductor. And because it's a conductor, again, we can make the same arguments. The value of the electric field must be 0. And by Gauss's law for the electric field, the total enclosed charge must similarly be 0. But I know that I have a charge Q. That means that since I know I have a charge Q, there must be a charge of negative Q contained on the surface. Again, I say on the surface because we already argued it can't be inside. And so good. Well, we could go a step further. We know that there must be a negative Q charge on the surface, the interior surface. Now let's go ahead and look at the rest of the problem. I say a spherical neutral conducting shell. Probably should be a comma there. Well, if the conducting shell is initially neutral and a value of negative Q ends up moving towards the interior surface, how much charge is left on the exterior surface? Yeah, good. Say, well, that must mean that there is a charge of positive Q on the exterior surface. And furthermore, it must be uniform. Pretty cool, right? Okay, good. Well, how about this? What happens if I offset the charge from the center? Go ahead, take a minute. Good? Yeah. And again, you know, okay, well, because I've offset the charge, now the distribution of charges on that inner wall should not be symmetric, right? I broke the symmetry by moving that interior charge. And so now we can throw out option D. And now we will go ahead and we'll have to figure out which option, A, B, or C. And here we'll again use this idea that we're dealing with conductors. The electric field inside the conductor is 0. In other words, there is no way for any of the charge on the outside of the conductor to know what's going on inside the conductor. The only thing that we do know is that there must be a net charge of Q on the surface. Well, since there's no way for the charge on the outside of the surface to know what's going on inside, right? The charges have rearranged in order that the electric field is zero inside the volume of the conductor. Because of that, the charge on the outside surface should uniformly distribute. Good. And so it turns out that even though we have offset the charge on the inside, the charge distribution on the outside remains unaffected. So it's kind of like the opposite, right? I said, hey, for this situation, there's no way for the charge or anything inside the conductor to know what's going on outside. But similarly, there's no way for charge on the outside of the conductor to know what's going on inside. Okay, so let's go ahead and work another example problem here using conductors. And this example, or the results of this example, we will use as we start moving into electric circuits and that kind of thing. Okay? And what it is that we would like to know what the electric field due to an infinite plane charge is. Okay, so we have a conductor, a really, really large conducting plate that we've dumped some excess charge onto, and we would like to know what is the value of the electric field produced by that charge arrangement. Okay. Now, as I've drawn here, and we can argue, the first thing that we draw is that the electric field must be perpendicular to the plate, and based on my coordinate system, must be pointing in the z hat direction. Now, you say, why is that? You can imagine that if I choose some field point, a distance z naught, above the surface of this plate, for every little chunk here, there is similarly a little chunk there, so that the x and y components of the electric field cancel out, okay? And the z components add. It's the same argument that we made when we were dealing with an infinite line distribution. We said, hey, there's a chunk here with the electric field going that way. There's a chunk here with the electric field that way. The horizontal components cancel, the vertical components add. Same idea, except now we're dealing with a two-dimensional object. So we have to think about those cancellations happening in 3 dimensions. Good. Well, as I've hinted at, we will go ahead and use Gauss's law for the electric field to figure out the magnitude of the electric field due to the infinite plane charge. Now here, I'm going to go ahead and draw a box. I want to pick a Gaussian surface whose n hat vectors are perpendicular to the direction of the electric field. So I've done a box. You didn't have to choose that. We could have, for example, done a cylinder, and the same ideas hold. Any n hat on the body of the cylinder is perpendicular to the direction of the electric field. Secondly, I would like this Gaussian surface to penetrate into the conductor, but not through. In other words, this bottom part of this box, I want it to be embedded inside the conductor. We'll see as we calculate out the net flux, we will see why that is advantageous. In fact, you already know. Well, if I want to calculate the net flux, because I have chosen an object with 6 different sides, 6 different n hats, I will go ahead and find the flux through each of the sides of the box. But here we will notice 4 convenient facts. I said that I'm choosing a Gaussian surface, and the n hat for the left and right sides and the front and back, the back one's hard to draw. You notice that the n hat for the sides of my box are all perpendicular to the electric field, which is pointing in the z hat direction. Well, what does that mean the flux of the electric field through those 4 faces is going to be? Good, 0. Lastly, what about the bottom? What is the magnitude of the electric field through that bottom face, which again is embedded inside the conductor? Yeah, good. The flux through the bottom also has to be equal to 0 because there is no electric field inside the conductor. So, although I've chosen a Gaussian shape that has 6 sides, the only side that I actually need to worry about is the top. Next question. Forgive me, I'll erase some of this notation now. Next question. What is the direction of n hat for the top face? Yeah, good. The direction of n hat for the top face is also in the same direction as the electric field. They are parallel. Furthermore, what can you tell me about the magnitude of the electric field? Again, I am dealing with an infinite plate. It does not matter my location, right? If I have an infinite plate, it doesn't matter if I'm located here or I'm located here or I'm located here. It's an infinite plate. It looks the same regardless of where my field point is located. The magnitude remains constant. And so I can write that the flux, the net flux through the entire Gaussian surface, is simply equal to the magnitude of the electric field times the area of the top surface. Cool? Now we would like to apply Gauss's law for the electric field. We have shown that the net flux is simply the magnitude of the electric field times the area of the top surface. Now we have to ask ourselves how much charge is inside that Gaussian surface that we've drawn. Well, you can imagine that intersection of our Gaussian surface with the conducting plane, it encompasses an area A. Right? This is why I drew the sides of my Gaussian surface being perpendicular to the conducting plane. Okay? I can say with confidence now that the area of the top of my box is the same area that intersects with the conducting plane. And since I know that the charge enclosed must be equal to the surface charge density, which is uniform. Why is the surface charge density uniform? Because I'm dealing with a conductor. Good, I drop it on there. It uniformly distributes on the surface in the absence of any other charges. Okay. So the enclosed charge, I can write it as being the surface charge density of the conducting plane times the area. Again, the area for the top is the same as the area that intersects the plane. And so I have a goody-goody moment. The areas cancel. And what I'm left with is that the magnitude of the electric field due to an infinite conducting plane is simply the surface charge density divided by epsilon naught. We will use this idea. Again, this idea will be very helpful when we start dealing with capacitors. Good. Well, that's all I have for you right now. We will now, after this, we will start stepping away from ideas about the electric field and we'll move into an easier quantity to deal with called the electric potential. So stay tuned. In the meantime, I thank you for your attention. Keep up the good work. I'll see you next time.